So our next speaker is Qirun Zhang from Georgia Tech, who's going to tell us about recursive state machine guided graph folding for context-free language reachability.
Hello, good afternoon, everyone, and welcome to the talk. And this is a joint work with my collaborators, Yuxiang and Yulei from University of New South Wales, and Hwei from Concordia University. I'm Qirun Zhang from Georgia Tech. So the title of our paper is a little bit long. It's called Recursive State Machine Guided Graph Folding for Context-Free Language Reachability. So in the title, there are three key concepts: context-free language reachability, recursive state machines, and graph folding. If we put together everything, essentially our paper proposed a technique called graph folding that can scale CFL-reachability computation by reducing the size of the input graphs. We use recursive state machines to specify context-free languages. The key technical insight of our work is try to understand the correspondence between the states in the recursive machines as well as the nodes in the graph. All right, let's first take a look at the first concept on CFL, context-free language reachability. CFL reachability is a well-known technique to formulate a lot of program analysis problems. A CFL reachability problem instance contains two parts. The first ingredient is a context-free grammar, CFG, which is used to specify an analysis problem that you want to formulate. The second ingredient is an edge-labeled graph G, which is the abstraction of your underlying program. For instance, say we have this context-free grammar, which essentially generates languages of properly balanced parentheses with arbitrary numbers of A's. And then the next ingredient is an edge-labeled graph. Note that all the edges in the graph are labeled by a character from the alphabet of the context-free grammar. As an example, if we take a look at the passes in the graph, for instance, we have a pass from node V1 to V5, and we can concatenate all the labels together along the pass, and then we will end up with pass strings. In this example, we have a pass string of open parens, A, and close parens. And it's obvious that this string belongs to the language that can be specified by the context-free grammar. In this case, we say that node 5 is as reachable from node 1, where S is the start non-terminal of the grammar. And the problem of context-free reachability is to compute the all pairs as reachable pairs in a graph. And there are also single source, single target variants, but our work focuses on all pairs reachability. So CFL reachability can be used to formulate a lot of program analysis problems, such as shape analysis and point analysis and type state analysis. The next concept is recursive state machine. Recursive state machines are extensions of finite state machines by introducing the concept of boxes. So you can treat each box as a function, so meaning that it can call other boxes and it can also be returned from boxes. So like in this example, we have a recursive state machine of M1 with its alphabet A, open parens, and close parens. It has only one local state because it has only one node. And in terms of global state, informally, it's just local state by taking the calling context into consideration. In order to recognize the strings, we need to define the initial states and the final state. And we also need to label those boxes. And it is important to note that RSM can also specify context-free languages. Indeed, it's equivalent to push-down automata. Therefore, ultimately, CFL reachability is equivalent to RSM reachability. For instance, it's easy to verify that this recursive state machine accepts the same string that can be generated from this CFG. So the next big question is that why do we need RSM? Our motivation comes from the observation that in the CFL reachability problem instance, we have an edge-labeled graph, and for the RSM, it is yet another edge-labeled graph. And both of the graphs are labeled by the same set of labels. Say, if we can build the correspondence between the states in the RSM and the nodes in the graph, then we can utilize our knowledge in RSM to simplify the graph. That's our motivation. So then we can move on to introduce our technique of graph folding. Informally speaking, The goal of graph folding is to reduce the size of the graph by folding the adjacent node pairs. For instance, here we have a graph, and suppose that if we want to merge the nodes x and y by removing the node y, then we end up with a graph with only 3 nodes and 2 edges. Formally speaking, given a RSM reachability problem instance, we want to generate a smaller graph G prime by folding node pairs in G and guarantee that G and G prime are reachability equivalent. As an example, here we have the RSM and the G that we saw from the previous slide, and the G prime is the output generated by graph folding. In this example, and we can merge 3 nodes V2, V4, and V3 into a representative V2 prime. And we can also merge nodes V5 and V6 into another representative node V5 prime. And if we list all the reachable pairs in the graph, we can see that node 7 is reachable from node 0 in both G and G prime. But the path string in G prime is slightly different from the path strings in G. Nonetheless, the path string in G prime still belongs to the language that can be characterized by the RSM. Therefore, the challenge in our work is to reduce the size of the graph. At the same time, we want to preserve the reachability information. The intuition of our idea is based on this observation. First, for every valid path in a graph, the path can always be mapped into a state transition chain in the recursive state machine. For this example, V0 can be mapped into the initial state, and Vk can be mapped into an accepting state Sk. And in the folded graph, if we want to preserve the reachability information, it's the same thing. So the last node Vk should be mapped into another state Vk prime. And in order to preserve the reachability information, Vk prime should be equivalent to Vk. And if we take a second look at this example, we can notice that the difference between the corresponding state transition chains in this example is that in the original graph, we have a state transition from Sy to S2, where in the folded graph, we have a transition from Sx to S2. So in order to preserve the reachability information, we wanted this state Sx to have a special property such that it can accept a valid outgoing transition L2, and the target state should be S2. And to sum it up, we can introduce this notation that is with respect to a label L2, and whatever state that can be reached by Sy, those states should be reachable by Sx as well. So by doing that, we can compute a set of states that is, for every node in the original graph, we can obtain a set of states in the recursive state machine. But unfortunately, we cannot compute this set Q because we cannot compute the CFL-reachability. Our technique is a graph pre-processing technique. And what we do here is that based on the edge labels, we can obtain all possible states in the recursive state machine introduced by this notation. Specifically, give edge labels in this example A and C, we can find all possible target state in the recursive state machine. In this case, we have this notation NR, set of NR, which contains N2, N4, and N5. As I mentioned, we cannot compute the ground truth, which is Qx, but instead we can over-approximate in Qs using the notation defined in the previous slide. And because the graph can contain cycles, so we have divided every situation into 4 cases. And due to the time limit, and I can only describe the first case. In this case, in order to preserve the reachability, what we want here is that first, for the first state, and we use the over-approximated all the global states, and then we follow two edges, Lxy and Lyx. And then the final state is this Sx prime. And according to the previous notation, what we want is that for all the states that can be reached by Sx prime, we want those states to be reachable by Sx as well. If that is the case, we can safely remove the node y as well as these two edges and still preserve the reachability consistency. That is the basic idea of our algorithm. We have implemented this algorithm and have tested it on two client analyses. One is value flow analysis, the other is alias analysis. And this slide shows the state machine as well as the grammar for the two client analyses. And we have tested, we have compared our algorithms against two other algorithms. SCC is based on offline cycle elimination, and InnerDiag is a technique to remove unnecessary parenthesis labeled edges. Because our technique is a pre-processing technique, so we utilize the state-of-the-art CFL-reachability solver, POCR. This slide shows the performance of graph folding on the first client application on value flow analysis, where the red curve shows the, the left figure shows the node reduction, and the right figure shows the edge reduction. And then the red curve shows the performance of graph folding. On average, we can achieve an edge reduction of 46%. And because the three algorithms are orthogonal to each other, so we can combine everything. So if we combine everything, we can achieve an edge reduction rate of 61%. And then this slide shows the performance on the second benchmark of alias analysis. And if we run graph folding alone, we can achieve an edge reduction of 35%. And if we combine everything, we can achieve graph reduction or edge reduction of 42%. Recall that our ultimate goal is to speed up the CFL-reachability computation. This slide shows the speed up rate. For the first benchmark, and we can speed up the CFL-reachability computation by 4 times. And for the second alias analysis application, we can speed it up by 3 times. And because we can reduce the size of the graph, we can also reduce the memory consumption by of the original algorithm. So on average, for the first client application, we can reduce the memory. On average, we can reduce the memory by 57%. On the second application, we can reduce the memory consumption by 65%. And our artifact is publicly available. Actually, we have the reusable badge. And our source code is also available on GitHub. And please feel free to check it out if you are interested in our work. And that's all for my talk, and thank you. I'm happy to take questions.
Thank you. Questions? Questions for our speaker? All right. So while people are thinking up their questions, I'll ask my question. So in your paper, you said that you have, when you're considering a folding pair, you have to over-approximate their corresponding states because it's too expensive to be precise. Yeah. So this presumably means that you miss some opportunities for folding that you might otherwise have, right? And I'm just curious, have you tried to estimate how much better you could be if you were precise? And so what fraction of the possible speed up are you actually obtaining?
Yeah, that's a very good question, and I believe that this is a very interesting future work, because as we see in this slide, like in this case, we have the ground truth, which is QVI, and we can actually obtain this ground truth by just performing CFL-reachability computation. And we didn't do that because our technique is a pre-processing technique, so that we, instead of analyzing the graph, we actually analyze the recursive state machine. And I think, yeah, thank you for the suggestion. I think it's very interesting to see how many the over-approximation rate, and we can also understand the situations where we cannot fold the graph and how to handle those corner cases, and in order to improve the further improve the performance of our graph folding algorithms. That's actually a very good suggestion. Thank you.
Great. Thank you.
Thank you.
Do we have more questions for our speaker? Okay, I see that we're in need of a new sugar boost. So, but in the meantime, let's thank our speaker. Thank you very much.